Hi, my name is Ben Botto. I'm a software developer and technical team lead for Benningfield Group in Folsom, California. And tonight I'm going to present about game hacking. And it's just going to be an introductory. I have my GitHub handle here at the bottom. I'm not going to dive into code too much tonight. But if you're interested, take a look at my GitHub process manipulator repository. It has code examples for everything that I go over tonight. And I did what I could to provide documentation and code samples for everything that we'll talk about tonight. So if you're interested in game hacking, take a look at my repository. I'm going to start off with a brief description of what game hacking is, and I'm going to do that with an example. Here I have a game called Assault Cube. Assault Cube is a multiplayer first-person shooter that's open source, OpenGL, and GPL. And for this demonstration, I've written an aimbot. The code is in my repository. It's just a basic aimbot. If I run it, you can see that my player has a bead on this other player here, the second player that I have running on my other laptop. And if I move that guy around, you can see that my crosshairs stay on the guy's head. So that's kind of what we're going to be talking about tonight. We're going to be talking about game hacking, modifying a game for which you have no source code, doing things like God mode, infinite bullets, aimbots, wall hacks, ESP, stuff like that, no recoil. So here's the topics that I'm going to cover. We're going to talk about tools. That's where we'll spend most of our time tonight. And we're going to talk about finding values in memory and the addresses of those values, both static values and dynamic values, and then reading and writing memory from code. And then next steps, after you learn to read and write. And we'll briefly talk about security, some of the stuff that gaming companies are doing. Most of the time spent tonight will be on a memory scanner. I use Cheat Engine as my memory scanner. There's some other ones out here. T-Search is one that I used to use. And there's ArtMoney, and if you're a Linux guy like I am, ScanMem is a command line memory scanner for Linux. But I like Cheat Engine. It has a ton of features. It's really robust. It's open source. I will say that if you install Cheat Engine, I recommend you install it from source, or if you download it and run the installer comes with some third-party software that you probably don't want. So make sure you go through the advanced installer and don't install the software unless you want it, the packaged software. You'll also need a C++ compiler. I've chosen to do this presentation in Windows for a couple of reasons. One is that most of the people that watch this are probably Windows users. There's probably 2 of you out there like me that use Linux. And the other reason is that there's a lot of games that run in Windows that don't really run in Linux. So I've chosen to do this presentation in Visual C++, or that's what my code examples are in. If you want to write game hacks, then you'll need a compiler that has inline assembly capabilities. G++ will work fine. I chose to use VC++ for this. You'll also need knowledge of C++ for reverse engineering video games. It's compiled code, but most games are written in an object-oriented programming language, and C is not object-oriented. So you need something with classes, and you need to kind of know how some compiled code translates to bytecode. So you need some knowledge of C++, so I emphasize not C, although knowledge of C is definitely helpful as well. And you'll need to know assembly, and you'll need a brain, because this stuff gets really complicated really quickly. Tonight we're just going to do a very brief introduction to game hacking. It's really simple stuff, but really quickly it gets very complicated. I mean, you're looking at compiled code and trying to find things like functions and structs and classes in compiled code. So that gets really difficult really quickly. So once you get more advanced, there's some other tools that can help you, like a debugger. Memory scanners usually have a debugger built in. Both Cheat Engine and T-Search certainly do, but they're not that powerful. So I usually use OllyDebug or GDB as a more powerful debugger. And then there's also IDA disassembler. I think that's a great disassembler, but oftentimes if you want to disassemble the game and look at it offline, you need a disassembler for that. So let's first talk about finding simple values. I say simple in quotes, not a technical term. It's just a term that I made up, but I call a simple value something that you can see on the screen. So if you look at Assault Cube here, you can see that I have 100 life. You can see that I have 19 bullets. So those are simple values. And so let's look at how to find these. First, you'll need to run Cheat Engine or your memory scanner, and it needs to be run as a administrator so that it can have debugging privileges with UAC. So if you click on this button here, you can open a process. I'm going to open a salt cube. And then here on the right, you can search for a value. I have 19 bullets right now, so I'm going to search for 19. I'm going to search for an exact value. There's some other stuff that can help you find ranges of values and so on and so forth. And I'm going to guess that the type is a 4-byte integer. I actually know that it is because I've already gone through this process a bunch of times, but it could be a float, like if you were looking for your location or your yaw or pitch or something like that, or a double or a string. So we're going to search for 4 bytes. So this searches through the game's memory and finds all these addresses that have a value of 19. If I go into the game now and shoot a couple of times, then I can search through this list of values for all values that are now 16, so things that have changed from 19 to 16. So that weeds it down to this one address. And if I add it to my list down here, I can change it to 100, say, and you'll see that that changes my bullets in game. So that seems to be the correct address. So I've outlined some steps, the steps that I just went through here on the slide, and I've posed a question at the bottom. What happens if the game is restarted? And I'm sure some of you know the answer, but I'm going to go ahead and restart the game. And now I'm going to reattach to the game with my memory scanner. And now you can see that this address, this address no longer points at 20, so it doesn't seem to point at my bullets. And the reason is that this player is on the heap, the player structure is on the heap, so bullets are on the heap along with that player structure. And so if I go through this scan again, the process that I just went through, search for 18 here, change this to the game, so one of these two values is my bullets. That one seems to be it. But you can see that the address is different now. And again, that's because it's on the heap. So there's a couple of reasons that it's on the heap. One is that objects are added at runtime to games. So a player may join the game at any time or leave the game, or things may die, come and go. So things are allocated dynamically on the heap. Second reason is that in C++, polymorphism only works with pointer types and reference types. It's not like Java where every method of a class is essentially virtual. In C++, you have to explicitly make methods virtual if you want to have an abstract class, and at late binding instead of static binding in C++ is something that's left to the programmer's discretion. But the point is that polymorphism, which is prevalent in games, only works with pointers and reference types. So let's take a look at this code here. This has nothing to do with the salt cube, just a code snippet that I wrote for this presentation. Here on the left, we have a player instantiated target practice. And if this player was declared in the main method or in some function, then this would be on the stack. If the player was global, it would be in the data segment. On the right here, we have a new player and a pointer to that new player. This new player is allocated on the heap at some available address, and this address will probably change every time you run the game or every time you run this code snippet. So this is on the heap, and this pointer, p_enemy, holds an address that points at the heap, but the pointer itself here, p_enemy, this variable, is on the stack, or if it's global, it would be in the data segment. And so if we can find this pointer in memory, p_enemy, not what it points to, but the pointer itself, then hopefully on successive runs of the game, the address will stay the same. And Cheat Engine provides a tool to do this called a pointer scanner, this automatic method down here. I'm going to go over this. And so we have our our address here of bullets. If you right click on it and do a pointer scan for this address, I'll talk about some of these options in a second here. But if we run it, you have to save it to a file. This is where the results will be saved. It'll run and it'll find a bunch of pointers to this address. So we have a bunch of them here, and oftentimes you'll have many layers of dereferencing. So here we have offset 0, but a lot of times this will have offset 1 and offset 2 and offset 3. And the reason is, if you've done any game programming or know anything about games, then you probably know that there's usually a complex class hierarchy in the games. For example, you may have a game that has methods like start and stop and pause and those types of things, and that could be on the heap. And the game may have something like a game world, which would also be on the heap. And then the game world may have like an array of entities, and that array may be on the heap. And then each item in the array, or list, or vector, or whatever, may also be on the heap, so each player. So you may have pointers to pointers to pointers to pointers to pointers in your hacking code. It's very common to have 5 layers of dereferencing before you can change a value. So here we kind of got lucky in the scan and found a bunch of values here that are only 1 layer deep. So you would have in this case, you would have a pointer to this address plus 150 bytes as a pointer to the bullets. So this would give us a pointer to a pointer if you're writing C++ code. I'm going to pick these 3 candidate addresses because these are in the AC client.exe module rather than on the stack. These look to be in the data segment. So I'm going to pick those, and they only have 1 level of indirection. And hopefully now if we restart the game, and then reattach to the game, these addresses will hold true. So they all seem to point to 20 now, even though this address has changed, the one from our last scan and the first scan. So if I change them, these seem to work. All 3 of these are candidate addresses. So now if we rebooted the computer, these pointers may change, or if you ran this, if you looked at this pointer here, one of these 3 pointers, it may be different if you ran this on a different computer. Cheat Engine provides some helpers for that. You can do a distributed scan if you have 2 computers networked together and verify that a pointer works in both environments. So there's some helpers for that, but here we found 3 addresses that are potential candidates. And again, if you use this in C++ code, because they have a pointer and then an offset from that pointer, you're going to have a pointer to a pointer in your code. You're going to have double dereferencing going on. If you have questions about that, you can come talk to me. I know that's kind of confusing. And then I also outline a manual method here of finding addresses. So you can, let's add this address manually here, 21EA2F8. So there's our bullets. This is the address that it points to. And you can add a watch to this, find out what writes this address, for example. So put a watch on the variable. And then if I shoot, we should see some instructions here, an instruction that changes the value. In this case, we decrement what's pointed to by ESI. The ESI register holds a pointer to our bullets. And so we can look at the disassembler here and analyze this assembly and manually find a pointer. So you can see ESI is accessed here. So we could go through that manually pretty quickly and find a pointer. And I'll tell you that the pointer scanner usually works pretty well, but sometimes it doesn't. And when it doesn't, manually analyzing the assembly always works. And it's just assembly. Everybody knows assembly. It's assembler is a simple language. So you can always analyze the assembly manually. And I've outlined some steps on how to do that here. If you're interested, you can come ask me about it. So next, what do you do once you have an offset and an address that works? I'll tell you this. If you know about operating systems, you already know this probably, but in Windows, Linux, Mac, whatever, addresses are virtualized. So, for example, if you build a program in Visual C++ and don't change any of the options in Visual C++, by default, the base address for that executable module will always be 400,000 hex, unless you change the linker options. And if you run the same program twice at the same time, both of those processes will have a base address of 400,000. And they're actually different regions of memory. They're just virtualized, so they appear to be 400,000, but really who knows where it is in RAM. The point is, you can't just write some code and make a pointer and expect it to write memory to another process. You can't write some hack code that points directly to a salt queue and modify the memory. Processes are isolated. It doesn't work that way. So you have to use some WinAPI functions to read and write memory from an arbitrary process. And so I've outlined some steps here. There's two handy functions, read and write process memory, that allow you to write to a foreign process. I have the documentation here on MSDN. It takes an address that you'd like to write to, a buffer of stuff to write, and how large the buffer is. And this first parameter is the tricky one, is a handle of the process. And so I've outlined some pseudocode, if you will, of how to get a handle to a process. This is one way, and it talks here about with UAC you have to have privileges to debug other processes, so your process has to have certain privileges, has to be run as administrator, so you'll have to deal with that too. But there's some instructions here on how to do it, pseudocode. Then if you look at my repository, there's some actual code, and my process manipulator class has an abstraction of this write process memory function that makes that easier. So reading and writing memory from an arbitrary process is kind of trivial as far as game hacking goes. Oftentimes, once you want to do something more complicated, so you want to run your code inside of another process. For example, you may want to make an aimbot that constantly aims at your enemies, or do some botting in World of Warcraft or something like that. So you need to get your code into the third-party process. And there's a couple of ways to do this. The best way to do this, in my opinion, is DLL injection. So you create a DLL and compile that in Visual Studio or whatever you use, G++, and then you force the arbitrary process, the game, to call load library and load your function into memory. And then you can do things like create threads right inside of that game's address space, or whatever you need to do, constantly aim, hook into the game loop. So my process manipulator library helps with that. If you're interested and you want to know how that works, it's pretty cool actually. There's some self-modifying assembly, so assembly code that runs and then modifies itself on the fly. It's kind of complicated, but really interesting if you're into that sort of thing. Once you learn DLL injection, there's some other stuff you can do. You can detour functions. This, for example, you find a function of interest in memory. Let's say you find the function that handles in-game chat. You could detour that function, so make it jump to a function that you control, and then in your function analyze the arguments, like analyze the chat that was sent by the player and see if it's maybe a command like /god mode on or something like that, and handle that command appropriately. And then if it's not a command, trampoline back to the original function. And so detouring functions, you could do it manually, or you can use a library to do it. Microsoft has a library called Microsoft Detours, and there's also some open source libraries to do that. Virtual method table overrides in C++, if you compile with Visual C++ at least, when you make a class, if that class is abstract and has virtual methods, then the first 4 bytes of the class in a 32-bit environment, the first 4 bytes is a pointer to the virtual method table, the V table, and it contains a bunch of addresses of functions that are virtual. And so you can make a class that is like a modified player class, for example, and maybe it has a shoot method. And if you find the shoot method in the virtual function table of your player, you can monkey around with that and manually implement polymorphism and have the game call your shoot method instead of the regular shoot method. So if you know a little bit about compilers and those types of things, it's really helpful. There's also OpenGL abuse if you've taken the gaming classes, gaming class on OpenGL. So just an example, you could call GL polygon mode and set the draw mode to GL lines, which would give you see-through walls, for example, or you could draw HUDs or radar, those types of things. So there's a lot of security techniques. We talked about function detours. This is a really common method employed by game hackers. They detour things like load library and write process memory and check if a function is called when it shouldn't be and flag you as cheating. Blizzard World of Warcraft and those types of things have great scanning processes. They scan all running processes, for example, and make sure that all the processes that are running are signed, and look for known signatures and window names, things like that. So if you load up Cheat Engine and hook into World of Warcraft, you're going to get banned for it. Valve also has Valve Anti-Cheat. There's Punkbuster, you're probably aware of. It takes screenshots. Most of these games have memory checksums. We call them memory checkers. They do a CRC on a part of the memory and make sure that it hasn't been modified. And if it has, if that checksum doesn't match up on the server side, then it flags you as cheating. If you know Linux security world, there's address space layout randomization. Every time you run the process, you get a different stack address. Windows has that now too. That's pretty easy to get around, but it's still an annoyance. And then now Intel has this software guard extension that allows code to run in a protected enclave that's encrypted, and this allows a developer to hide code in memory. So this will really affect game hacking and just hacking in general. It's a double-edged sword here. This would allow a game developer to hide, for example, a player structure in memory, and a hacker would not be able to see what's in that memory. It's encrypted. But likewise, a hacker could write some hack code and hide it from the game. So something like the Warden in Blizzard would not be able to analyze that code. So it's kind of a double-edged sword, but it's really, really interesting if you want something to read about. So anyway, that's what I had to talk about tonight. Here's my contact information. Feel free to email me if you have any questions, or come and talk to me. And take a look at my repository. If you have any comments about that, let me know. Thanks for watching.